Welcome to the Things of the Stars, Sleeping with Science series. These journeys invite you to slow down, quiet your thoughts, and drift into rest while exploring the wonders of the universe. If you enjoy these moments of calm discovery, support us by subscribing to this channel and visiting thingsofthestars.com. Imagine the deepest silence before any stars were born, a darkness before light existed. In this hushed void, we confront one of the greatest mysteries: what came before the Big Bang? It's a question that borders on the poetic and the philosophical, yet scientists have dared to explore it. In this gentle journey, we'll float through scientific and philosophical perspectives on what might have preceded the birth of our universe. We will encounter ideas of time beginning or cycling, of universes bouncing and multiverses budding, told in plain, dreamy language to lull you towards sleep, even as we ponder cosmic origins. We know that our universe is expanding. If we rewind the cosmic film, everything we see, galaxies, stars, space itself, gets denser and hotter as we go back in time. Eventually, we reach a point about 13.8 billion years ago when the universe was an infinitesimal point of extreme density and temperature. This is the Big Bang, in conventional cosmology, an initial fireball out of which space and time as we know them emerged. However, if we try to push earlier than the first instance of the Big Bang, our trusty physics equations falter. In the framework of Einstein's general relativity, the math predicts a moment of infinite density, a singularity, at the start of the Big Bang. Infinity is usually a sign that a theory has broken down. It tells scientists that relativity on its own can't describe that earliest moment when the universe was fantastically small and energetic. As one scientific American article put it, at that Big Bang singularity point, space, time, matter, everything is compressed to a point where our current laws of physics no longer make sense. In other words, the Big Bang, as described by classical physics, is not so much a beginning of the universe as it is a boundary of our understanding. Imagine a serene cosmic scene stretching out before us with deep blue starlight and swirling clouds of galaxy dust. Imagine time flowing outward from a single bright point at the center, a metaphor for the Big Bang radiating space and time into being. At the very beginning, all that we know was condensed in a tiny seed ready to blossom into the cosmos. So what do scientists do when the equations hit a wall? They seek new theories. In this case, quantum gravity is the sought-after key, a theory uniting quantum mechanics which rules the tiny scale of particles with gravity and cosmic geometry. We don't have a complete quantum gravity theory yet, but many physicists are working on it because it would let us peer further back to understand what happened at time zero and perhaps before. Without it, asking what came before the Big Bang is like staring at a blank screen. Our current physics just doesn't play the frames from earlier. As physicist Sean Carroll explained, classical general relativity can tell us a lot after the bang, but it can't prove anything until after the Big Bang occurred. To go earlier, we likely need the fuzzy, probabilistic rules of quantum physics to blend with spacetime. It's important to remember that before the Big Bang might not even be a sensible phrase in ordinary terms. Time itself could be a result of the Big Bang. This brings us to the first perspective. Maybe time had a starting point, and talking about a time before that is as meaningless as going further south than the South Pole. One elegant resolution to the Big Bang mystery is that there was no before, because time began with the Big Bang itself. This idea was championed by Stephen Hawking and James Hartle in their no boundary proposal. They suggested that the universe might be finite, but without a boundary in time, somewhat akin to the Earth's surface. The Earth is finite, yet has no edge. You can't fall off, and there is no starting or ending point on the surface. Hawking applied this analogy to time. He famously said, asking what came before the Big Bang is like asking what lies south of the South Pole. It's a question that simply doesn't apply because time didn't exist north of that origin point. Think of the beginning of the universe not as a sharp point, but as a smooth cap or dome. In Hawking's model, the early universe can be imagined as shaped like a shuttlecock or a rounded globe. At the very bottom, time is fuzzy or non-existent. Only space exists in a kind of primordial, timeless state. As you move up, analogous to moving forward in what we perceive as time, the universe expands and the familiar arrow of time emerges. In this picture, time unfolds from a timeless state, the way the first light of dawn emerges from the darkness, gentle and without a sudden jump. The phrase "no boundary" means there is no hard border where time starts. Instead, time smoothly comes into being. Hawking's colleague Jim Hartle explained it like this. In the very early universe, there was no distinction between time and space. Time as we know it crystallized later. What does this mean for before? It means there was no before the Big Bang, at least not in the sense we think of time. The Big Bang wasn't an explosion in time. It was the coming into existence of time itself. This idea is profoundly counterintuitive. Our minds keep wanting to ask what caused that and what was before that. According to Hawking's no boundary idea, those follow-up questions are moot. Time is like a loop that closes back on itself. There is no outside the loop and no prior to the beginning any more than there's a step before the first step on a circular staircase. This perspective is appealing in part because it sidesteps the need to explain a cause or a prior state. It says, effectively, that the universe could have arisen from nothing without violating any rules, because nothing is not a point in time, but rather a state lacking time. Hawking put it succinctly Asking what came before the Big Bang is meaningless. It would be like asking what lies south of the South Pole. In a bedtime story sense, we could imagine the Big Bang as the first moment of time, like the opening note of a grand cosmic symphony that has no overture before it. It just begins, and time begins with it. This idea, however, is just one view. Not all physicists are convinced that time had such a neat beginning. Others wonder if perhaps the cosmic symphony had a prelude, some earlier movement in the grand musical score of reality. Next, we explore those ideas, universes that cycle or bounce, so that perhaps the tune of existence had been playing already before our movement began. What if the Big Bang wasn't the first bang? What if it was more like a phoenix moment, the rebirth of a universe from the ashes of a previous one? This idea of a cyclic or bouncing universe is deeply alluring and actually quite old. Ancient cultures, such as in Hindu cosmology, imagine time as an endless circle of creations and destructions. Remarkably, modern cosmologists have echoed some of those ancient ideas. Alexander Vilenkin noted that Hindu philosophers millennia ago speculated about an eternal universe and a cosmic egg, cyclical creation. In the 20th century, some scientists like Richard Tolman considered an oscillating universe that expands, then contracts under gravity into a big crunch, which might then trigger a new Big Bang, and so on forever. Classical oscillation ideas ran into issues, but the core notion survived in new forms. One modern variant comes from quantum gravity theories. For example, physicist Martin Bourgeois, working in an approach called loop quantum gravity, has proposed that a previous universe could have imploded and then exploded into ours, meaning the Big Bang was really a big bounce. In loop quantum gravity, space and time are not infinitely divisible. There's a smaller scale, like fundamental atoms of space-time. When a collapsing universe reaches this incredibly tiny scale, quantum pressure builds up, analogous to the way atomic physics can make matter resist being infinitely compressed. Instead of an ultimate collapse to a point, quantum effects cause a powerful bounce and the universe begins expanding again. Cosmologists refer to this dramatic rebirth as a bounce rather than a bang. If this is true, then our universe existed in a different form before the Big Bang. It was a previous universe, contracting, shrinking perhaps from something vast down to something very small, until the bounce reversed the collapse into expansion. What was that previous universe like? Here's the catch. It might have been very similar to our own, or utterly different, but almost all traces of it would have been erased in the violence of the bounce. The equations suggest that the extreme quantum chaos of the bounce would wipe out specific details of the earlier state. It's as if the universe completely forgets its past life when it starts anew. Only very general traits could carry through. This cosmic amnesia means even if there was a before, it might be nearly impossible to retrieve any information about it. To our minds, it effectively might as well be a new universe, except that it provides a natural explanation for how a bang can happen without coming from truly nothing. It came from a prior contraction. Another captivating cyclic idea comes from the renowned physicist Roger Penrose, a Nobel laureate who, even in his 80s, has been imagining new ways the universe might recycle. Penrose's theory is called conformal cyclic cosmology. The gist of it is mind-bending yet poetic. He proposes that the remote future of our universe, trillions of years from now, after all stars have died and all matter has decayed, will in a strange way transform into the Big Bang of a new universe. How could the end become a beginning? Penrose's insight is that in a universe that has expanded so much that it's nothing but diffuse radiation, the concept of time. In this theory, each universe expands and thins out until it reaches a kind of horizon of eternity, and then, through a mathematical twisting of geometry, that final horizon of one universe becomes the starting point of a new universe. In more visual terms, think of each universe as a great balloon. Penrose says, if you squint at the physics just right, the surface of an infinitely large, empty balloon can be identified with a single point, which could serve as the seed of a new balloon. It's a bit like saying the very old universe at the end of time morphs into an infant universe again. Penrose's cyclic cosmos doesn't bounce back in the traditional sense. It doesn't collapse. It just stretches out to almost nothing and then reboots. He even claims to see hints of previous eons in patterns of the cosmic microwave background, the afterglow of our own Big Bang, such as mysterious circular hotspots he calls Hawking points that might be traces of black holes from a prior universe. Not all scientists agree that this evidence is valid, but it's fascinating that such tests are even being attempted. Beyond these, there are other cyclic ideas too. One notable model inspired by string theory is the ekpyrotic universe. In that scenario, what we think of as the Big Bang was caused by a collision between two giant invisible brane worlds in a higher dimensional space. Imagine two nearly flat sheets drifting in a 5-dimensional space. Once every trillion years or so, they collide, and the impact releases stupendous energy enough to create a hot Big Bang and a whole new universe on each brane. Then the branes recoil. The universes cool and evolve, only to perhaps collide again much later. It's an exotic twist on cyclic cosmology that extends the idea of cycles into extra dimensions. In all these cycles and bounces ideas, the Big Bang is not a singular one-time event. Instead, it's part of an ongoing, perhaps endless, drama. The universe could be far older than the Big Bang. With epochs of time we can barely imagine. This is a comforting thought in a way. Creation is not a one-time miracle, but a repeating heartbeat of reality. If true, before our Big Bang, there was another world, another chapter of existence. However, these theories face their own challenges. For example, entropy or disorder tends to increase in closed systems. So how do you reset the entropy each cycle? There are also new questions. If the universe is cyclic, why don't we remember past cycles? And of course, we lack direct evidence of a pre-Big Bang phase. No stars or relics clearly survived from before. These ideas are compelling, but still speculative. Still, the cyclic view resonates with something deep. It portrays time not as a line with a start and end, but as a circle or an endless spiral. Many find a poetic symmetry in that. Just as day follows night in a cycle, perhaps universes follow universes. With that thought, let's shift to another bold idea. Maybe our Big Bang was not alone, but one of countless bangs popping like fireworks in a grand cosmic display. This is the realm of the multiverse and eternal inflation. Our current best theory of the very early universe is called cosmic inflation. Proposed by Alan Guth and developed further by others, inflation suggests that a tiny fraction of a second after the Big Bang, the universe underwent a phenomenally rapid expansion, doubling in size over and over exponentially so that something microscopic blew up to astronomical scales. Inflation was invented to solve mysteries like why the universe is so uniform on large scales. Inflation answers this by saying our entire observable universe grew out of a small, smooth patch that got stretched flat and smooth before irregularities could grow. Inflation, if true, is an add-on to the Big Bang story. It's what happened right after the Big Bang, shaping the initial fireball's expansion. But here's the crazy part. Inflation might not stop at just creating our universe. Many physicists realize that inflation is a process that, once started, can continue endlessly in other regions. Think of inflation as a field or energy that fills space. In some places, it might slow down, but elsewhere it can keep going and going. As it goes on, it creates new bubbles or pockets, and each of those pockets could become a universe of its own, with its own Big Bang and expansion. This is often called eternal inflation. In eternal inflation, space as a whole is stretching and creating more space at stupendous rates, and here and there, little bubble universes pinch off like droplets from a vast foamy ocean. We live inside one such bubble. Our Big Bang was essentially the formation of our bubble universe, produced as inflation in that region ended. But outside our bubble, inflation kept going, creating other bubbles, an ever-growing multiverse of universes. Some bubbles might collide or influence each other, but generally they are far apart, each expanding internally with their own space and time. If this picture is correct, then asking what came before the Big Bang might be like asking what was happening outside our bubble, or what was the larger space in which our universe was born. The answer would be that inflation was happening. A sort of meta-universe was there, endlessly creating new universes. The multiverse idea is breathtaking. Our entire universe, with its billions of galaxies, could be just one grain of sand on an endless cosmic beach. And each grain might have different properties or even different physical laws. Some cosmologists describe eternal inflation as a universe generator. It doesn't need a traditional start. It goes on forever forward in time, spawning new universes infinitely. But what about past time? Did inflation go on forever in the past as well? Guth, Lindy, and Vilenkin pondered that, and in 2003 they proved a theorem that even an inflating universe cannot be eternal into the past. It had to have a beginning. In other words, inflation may be eternal going forward, but it cannot be stretched infinitely backward in time. There must have been some start to the inflating space, some initial moment. This suggests that the multiverse itself had an inaugural Big Bang of sorts, not necessarily a single point, but perhaps a quantum event that launched inflation. What could have started inflation? That's an open question. One idea is a quantum fluctuation triggered inflation. Another is that inflation might start in a high energy condition that itself requires explanation. We don't yet know. If the multiverse exists, before our Big Bang could mean the process or condition that allowed our bubble to form. For instance, maybe a patch of inflating space cooled and dropped out of inflation, like water freezing into a crystal, and that phase transition was our Big Bang. The space around it might still be inflating now, creating other universes. Imagine an antique cosmic clockwork with golden gears and rings interlocking against a starry backdrop. If the universe runs in cycles, or if there are many universes ticking away, imagine each gear as a cosmos, turning eternally. Such imagery helps us picture the multiverse or cyclic time as a grand, orderly mechanism, even if in reality, it's far more chaotic. Some scientists, like Sean Carroll, have speculated that a multiverse could also solve the riddle of time's arrow. In a single, isolated universe that lasts forever, eventually, things run down. But in a multiverse that continually sprouts new universes, there's always a fresh, low entropy bubble beginning somewhere, so there's no ultimate equilibrium. In simpler terms, each new universe is like a baby with renewed orderliness, so the overall multiverse never completely dies out. This is a speculative but appealing answer to why time keeps flowing and hasn't ground to a halt. The multiverse idea is hard to verify. It moves the question of origins up one level instead of what came before our universe. It asks, we don't have that answer yet. It might be that the multiverse just is always existing in some form. Or perhaps even the multiverse emerged from a yet higher level phenomenon. One can get dizzy thinking of the nesting of realities. Nonetheless, eternal inflation provides a scientifically grounded scenario in which our Big Bang was not the beginning of everything, but rather one chapter in an endless cosmic novel. Before our chapter, there were others, and after, there will be more. Now, let's step back from multiple universes and look at something equally perplexing but in a different vein. Could the universe truly arise from nothing at all? And what does nothing even mean in the context of quantum physics? In the realm of quantum physics, nothingness isn't really nothing. Even what we call a vacuum seethes with energy and particle-antiparticle pairs flickering in and out of existence. It's like an empty field that still has a faint, restless whisper. Some physicists have applied this idea to the entire cosmos. Perhaps the universe tunneled into existence from a state of no universe. If that sounds impossible, consider that on small scales, quantum rules allow particles to appear without a cause as long as they disappear quickly. There's even a saying, the universe is the ultimate free lunch, meaning quantum mechanics might permit the sudden appearance of the universe from nothing, balanced by positive and negative energy so that no conservation laws are broken. Alexander Vilenkin, one of the pioneers in modern cosmology, has advocated a model of quantum creation of the universe. He wrote a paper in the 1980s about the universe coming from quantum tunneling out of literally nothing, no space, no time. It's hard to picture no space, no time. Our brains recoil at the concept. But mathematically, one can define a nothing as a state with no classical space or time, yet governed by whatever fundamental laws still apply. From this state, there's a certain probability that a tiny closed universe will spontaneously appear, a bit like how a particle can pop out of the vacuum. Once the universe appears in a tiny nascent form, inflation could take over and blow it up to macroscopic size in a flash. Vilenkin explains that in quantum physics, events do not always have a definite cause. Instead, they have probabilities. So, he says, there is a non-zero probability that a tiny universe will form out of nothing. From essentially nothing, you get something, in fact, everything, due to a quantum leap. Once that little bubble of space-time exists, it can grow if it has the right properties and vacuum energy to inflate. This is a bit like a spark appearing in the dark with no hand striking a flint. It just happens, rarely but inevitably, given enough time, though there was no time before time. Even Stephen Hawking considered this idea in his later work. In fact, Hawking's no-boundary proposal was a specific way of calculating that probability amplitude for the universe's wave function, essentially an attempt to answer how a universe can emerge from nothingness in a smooth, natural way. In Hawking's view, the laws of physics themselves could be the spark that ensures a universe will appear. He famously said that with gravity, the universe can and will create itself from nothing, a statement that caused much philosophical debate. To be clear, nothing in these discussions doesn't mean an empty void in which the universe appears. It means no void at all, no space for a void, no time for things to exist or not exist. It's a state we can't really find words for, since even state is a concept within time. But the mathematics of quantum cosmology provides a vocabulary for this through something called the wave function of the universe and imaginary time. The end result is a concept that the Big Bang might have been a quantum fluctuation, analogous to a particle materializing out of the vacuum, except this particle was space-time itself. The quantum creation idea shifts the question, what came before, into what underlying laws or principles allow time and space to emerge. It could be that before the Big Bang, there was a timeless quantum realm, not a pre-universe in time, but a more fundamental reality out of which time and universe can spring. Some liken this to an artist's blank canvas or the surface of calm water before a ripple. Then, a fluctuation akin to a random small ripple triggers a cascade that becomes a new expanding universe. If this sounds philosophical, it is. It's at the edge of what we consider science because it's hard to test. Yet it's an area of active research. Physicists are trying to connect models like this to potential observations. For example, certain subtle patterns in the cosmic background radiation might hint at an exotic birth of the universe. So far, no conclusive evidence has singled out one theory of the beginning over another. But these ideas give us plausible answers consistent with physics as we know it. Notably, if the universe can start from nothing due to quantum rules, that also might answer the age-old question, why is there something rather than nothing? The answer would be, because nothing is unstable. Given enough chance, something will eventually pop out. As one physicist joked, nothing is the fastest decaying state. From this point of view, perhaps the default is not an empty void, but the constant bubbling of possible universes. We just happen to inhabit one that caught on and evolved stars and galaxies. Let's turn to a concept we've mentioned a few times, entropy and the arrow of time. This might seem like a different topic, but it's intimately tied to the question of the universe's origin. Entropy is a measure of disorder or randomness. A high entropy state is very disorganized. A low entropy state is very. One of the fundamental laws of physics, the second law of thermodynamics, says that in any closed system, entropy tends to increase or at least stay the same over time. That's why eggs scramble, but never spontaneously unscramble, why we grow older and not younger, and why the stars exhaust their fuel eventually. This gives time a direction. We always move from lower entropy to higher entropy. This one-way street is the arrow of time. Now, here's the puzzle. The Big Bang state was an extraordinarily low entropy, highly ordered state. Think about it. The universe began extremely hot and dense, which sounds chaotic, but in fact it was smooth and uniform in every direction on large scales. Smooth and uniform is actually a state of low entropy for gravity, all the matter evenly spread out rather than clumped. The famous physicist Roger Penrose once estimated how special the Big Bang was. The odds of such an ordered state happening by chance are incredibly small. As philosopher of physics, Tim Maudlin explained, the fact that the universe started in this peculiar, very organized way seems highly improbable and begs for an explanation. It's as if someone prepared pristine initial conditions. This is sometimes called the past hypothesis, that the universe began in a special low entropy condition, which is why we have an arrow of time. If the Big Bang was the absolute beginning, one might shrug and say, well, that's just how it started. But scientists are not usually satisfied with that. They'd like to know why it started so orderly. This is where the idea of a before can become attractive. If something came before the Big Bang, perhaps it set up the initial conditions. For example, in cyclic or bounce models, maybe the previous cycle ended in a very smooth, spread out state. Or in inflationary models, inflation has the effect of wiping out irregularities. It resets the clock by creating a smooth patch that becomes a new universe. Inflation by itself still needs an initial trigger, but once it happens, it produces a low entropy starting point. Sean Carroll, in a talk about time, said that the early universe shows it to be hot, dense, and smooth over a wide region of space, and that our universe just doesn't look natural. He went on to say, this smoothness is a bigger surprise than even the mysteries of dark matter and dark energy. It's an enormous clue that must point to something. One interpretation is that maybe the universe we see is just a small part of a bigger system, which was in a more typical state, and our patch happened to get a low entropy start. This is essentially the multiverse explanation. We live in a bubble that, by chance or selection, started off very orderly, allowing life and complexity, while the multiverse at large can be maximal entropy overall. In a sense, many universes could exist with random conditions, and naturally, we find ourselves in one of the rare orderly ones because only those can harbor observers like us. Alternatively, if time is cyclic, perhaps the arrow of time can reverse, or time can loop such that the end of one cycle feeds into a new low entropy beginning. It's tricky to violate the second law, but some models avoid it by effectively emptying out the entropy at the turnaround. Another idea is that our universe might be one side of a two-sided cosmos, where another universe stretches out in the other time direction from the Big Bang. Think of the Big Bang not as a single arrow launching upward, but as a point from which two arrows shoot out in opposite directions. Time goes forward for us on one side, and perhaps another universe experiences time forward on the other side, which to us would look like before the Big Bang. In that scenario, the Big Bang is a kind of mirror point of lowest entropy between two symmetric time directions. So each half sees the other half as before their own Big Bang, in a sense. This is a highly speculative idea, but it's a clever way to address the entropy problem without needing a singular beginning. Instead, the beginning is a bridge between two time arrows. To make the idea of low entropy more intuitive, Carol offered a homely metaphor. Every time you break an egg or spill a glass of water, you're doing observational cosmology. Because those one-way processes ultimately trace back to the conditions of the universe's birth. If the cosmos hadn't started in such a low entropy state, we wouldn't have this marvelously directed arrow of time along which complexity can build and life can evolve. So in a bedtime reflection, we might say the entropy and arrow of time issue is a hint that the Big Bang was not a random moment, but something that might demand a prior explanation or a special mechanism. Summing up, the arrow of time is one of the reasons cosmologists even entertain before the Big Bang ideas. It's a clue in the dark, suggesting that perhaps what we see as the beginning might have been set up by something we can't see. Whether that was a previous cosmic cycle, a multiverse environment, or a quantum pre-time, we don't yet know. At this point, it's clear that what came before the Big Bang is not just a scientific puzzle, but a deeply philosophical one. We are stretching the limits of what science can say, since we have no direct observations of before. It tickles the brain with paradox. If time began, how can we speak of before time? If cause and effect began, can there be a cause of the universe? These are questions that echo through philosophy of cosmology and even theology. Even scientists sometimes slip into philosophical contemplation here. For instance, the notion of a universe with a beginning can make us wonder what caused that beginning. Some see in that a hint of something beyond physics. Alexander Vilenkin noted that for many physicists, the beginning of the universe is uncomfortable because it suggests that something must have caused it. In fact, we now have models where that's not necessary. The universe spontaneously appears, quantum mechanically. In other words, modern cosmology tries to provide a self-contained explanation so we don't require an outside cause. Whether that's successful is still up for debate. But it shows the effort to make sense of a beginning in scientific terms. Another philosophical aspect is the idea of time itself. We take for granted what time is, a flowing river carrying us from past to future. But the question of a beginning of time forces us to confront the possibility that time might be more like a circle or a dimension that can bend and even have an origin point. If time started at the Big Bang, the question what happened before might simply be categorically invalid, a type of question that has no meaning, like asking to draw a shape with only one side. Some philosophers argue about whether the universe had to have a beginning or could be infinite. There's even a famous cosmological theorem which in plain language says, under reasonable assumptions, time cannot be infinite going backwards. There must be some boundary. But assumptions could be wrong. Maybe there are loopholes. If a loophole is right, time could be eternal after all. If not, time is finite. We're also forced to wrestle with what nothingness means. Philosophers have long asked, why is there something rather than nothing? And now cosmologists join that discussion with equations and models. Some propose that nothing would have been unstable, that nothingness would inevitably give rise to something due to quantum laws, as discussed. Others point out that's just moving the question, why do quantum laws exist? Why is there a false vacuum that can fluctuate? These might be unanswerable in empirical terms. They might always lie at the boundary of human explanation. Every time we find an explanation, we might still ask why that fluctuation, why those laws. It becomes a chain that perhaps has no end or loops unto itself. From a poetic standpoint, one can also think in metaphor. Maybe the universe is its own parent. Some speculative proposals even suggest closed time loops where the universe creates itself. This is hard to formalize, but it captures the idea that the explanation for existence might be circular in a self-consistent way. A bootstrap cosmology where the universe bootstrapped itself into being. This might sound like science fiction, yet when dealing with time and causality at cosmic scales, we cannot fully rule out such peculiar possibilities. It's also noteworthy that all our theories, as sophisticated as they are, still might be incomplete. A philosopher might ask, are we sure we even know how to pose the question right? Perhaps before the Big Bang is like asking a fish what's outside the water. It lacks context. Some thinkers suggest that new concepts of time might be needed. Time could be emergent, a secondary phenomenon arising from something deeper, like how temperature emerges from the motion of molecules. If so, talking about before time might be like talking about before a certain phase transition, meaningless because the concept didn't exist yet. Ultimately, we must have some humility. We've journeyed through many speculative universes tonight, bouncing cosmologies, infinite multiverses, quantum foams, and timeless voids. Which, if any, is true? We do not yet know. Possibly, the truth could be none of the above, or something we haven't even imagined. The great physicist Sir Arthur Eddington once said, "Something unknown is doing. We don't know what." And that might be a fair description of the state of things before the Big Bang. At the end of our exploration, What have we learned? We've learned that there is no shortage of awe-inspiring ideas about what came before the cosmic dawn. Science and philosophy together paint a picture of many possibilities. Time might have simply begun, rendering before meaningless. The universe might cycle through eons, each Big Bang a renewal from a previous end. Our Big Bang could be one bubble amid an eternally inflating ocean of universes. The cosmos could have quantum tunneled into existence from a timeless nothingness. And there are hybrid ideas like mirror universes or self-created time loops that push the boundaries of imagination. For now, we have hints, but no definitive answer. And that's okay. The question of what came before the Big Bang may ultimately be something we approach without ever fully reaching, like an asymptote in mathematics. But in trying to answer it, we've deepened our understanding of the universe's earliest moments and of time itself. As you lay here under the metaphorical canopy of stars, consider the quiet grandeur of this mystery. Our universe, with all its galaxies and wonders, erupted from we don't quite know what. Yet here we are, children of that origin, able to ask the question. In a way, we carry the answer within us, since the stuff that makes us was forged in the Big Bang, and whatever preceded it. We are made of star stuff, as Carl Sagan said, but also of Big Bang stuff, and maybe even before the Big Bang stuff, if any of these theories hold true. There's a profound poetry in not knowing. It leaves room for imagination and humility. The renowned cosmologist Alex Vilenkin admitted, "I cannot really claim that I understand the beginning of the universe. We have a picture which kind of makes sense, which I think is an achievement." Science has given us pictures, bouncing universes, cosmic eggs, inflationary multiverses, each like a fragment of a grand cosmic dream. They may not be the final truth, but they light up the darkness a bit. So, what came before the Big Bang? Perhaps an earlier universe, perhaps nothing at all, perhaps an infinity of other universes, or a timeless void. Each answer is mind expanding. As we close our eyes, we might imagine the Big Bang not as a harsh flash, but as a gentle dawn. Before any dawn, there is night, but what a strange night that would be without time or space. It's a realm we can hardly fathom. And so, perhaps we let go of trying to fully fathom it. Feel the comfort that in this enormous unfolding story, mystery itself has a place. Our not knowing is part of the tale. Maybe one day, far in the future, humans will uncover more pieces of this puzzle. But tonight, it's enough to float among the ideas like stars drifting in the sky of mind, and to accept the uncertainty. In the end, the question of before the Big Bang teaches us that beginnings might be new, beginnings of something older, or that some questions lead to deeper questions without end. Either way, the quest is beautiful. As you drift to sleep, let yourself feel the wonder of it. The universe is vast in space, but also in time, and possibly beyond time. We are small, but we are curious, and our curiosity is a way for the universe to reflect on itself. In the quiet of your thoughts, you might imagine the cosmos as a great breathing entity. Each big bang an inhale, each end of a universe an exhale, endless and serene. Or picture a calm ocean at night, dark and still. Then a single wave rises, spreads, and settles back, only for another to rise elsewhere. These are just images, attempting to lull the mind into grasping the ungraspable. Finally, let's embrace a simple truth. Right now, this universe is here, and we are in it. Whatever came before, it led to this moment. Perhaps the greatest miracle is not what preceded the universe, but that we have a universe at all, a stage on which stars shine, life grows, and minds can wonder. The fact that we can ask the question is itself a small triumph of the cosmos. So, as we conclude this journey, feel free to let the specifics melt away. You don't need to solve the mystery tonight. It will be there tomorrow, and scientists will keep chipping at it bit by bit. For now, it's time to take comfort in the darkness, much like the darkness before the dawn of time. In this peaceful state, unknowing is not scary, but gentle. We started with a question, and we end with a lullaby of possibilities. The universe cradles us, and the mystery of before the Big Bang rocks us into contemplation. Close your eyes and drift among the stars of possibility. In this vast and timeless moment, let yourself be content with the wonder and let sleep come.